In today's video, I want to talk about local response normalization, a technique also called brightness normalization. It's seen in papers like the one showcasing ImageNet classification with deep convolutional neural network. I want to talk about it since it's related to my field of study, which is neuroscience. I'll first talk about the formula so that we have a clear understanding of what it's doing. Then I'll show you how neurons are actually kind of doing the same. The formula has been taken from the AlexNet paper and it looked like this. Let's break it down piece by piece so that everything make more sense moving forward. The upper script means the indices of the kernel maps. So local response normalization is manipulating different neurons in different kernel to normalize their output. So they are within different two-dimensional kernels. So the underscript in the formula represent the x and y position of the neuron on all kernel maps. So this method acts on the same neuron, so the neuron in the same position on multiple kernel maps. So b, x, y, upper script I is the local response normalized output from a neuron at x, y for the kernel I. So a, xi, upper script I is the output from the activation function of the neuron at position xy of kernel I. So this activation function is then divided by this huge chunk to yield the output b. So there are four parameters that need to be set using cross-validation. So we have k, which acts as a bias. We have alpha, which multiply the summation that you see over here. We have beta, which scale the whole normalization. And finally, we have n, which is a parameter to see how deep in the order kernel we need to take into consideration. So if the n was 10, there will be 10 neurons in 10 different kernels that will be used for the normalization. In the AlexNet architecture, the value for each of these parameters was found to be good enough at k equal 2, n equal 5, alpha equal 10 to the power minus 4, and beta equals 0.75. So the summation looks like this. The idea behind the summation is simple. Taking the current neuron in consideration, we look at n divided by 2 below and above it in kernel space at neuron in the same position. So the max and min that you see over there is just to avoid the corner cases to get to negative subscript or subscript overflowing. So the whole thing is simple. We just simply sum up the square of the ReLU activation of each neuron within this kind of column of kernel. And that's it. This is the whole thing. So what this will do is that the neuron with the strongest activation among neighboring neurons will be even greater, thus kind of drowning the other neuron activation. So let's now look at what is happening in the brain for real. So local response normalization is inspired from the phenomenon called lateral inhibition that happen in real neuron. So the gist of it is that the same neuron in the cerebral cortex or the thalamus will actively inhibit a neuron in the lateral direction when they output an action potential or a graded potential. So this phenomenon happens mainly in the sensory processing neuron as a way to reduce noise and increase signal-to-noise ratio. This happens for the visual system, mainly at the retina, but also in the tactile, auditory, and olfactory system. It's somewhat like a universal trick of the brain to sharpen its information processing. So this inhibition doesn't only happen at one level of processing, as we will see in the visual system. It happens from on the retina at various layers of neuron. So let's take a look at the process in the retina. All right. So I'm gonna first go through like the path that the light is going through in the retina, just so that you understand who the players are and what's happening. And then I'm gonna explain a bit more where the lateral inhibition is actually happening and the link with the local response normalization. So the light enters over here on the left, so it goes through the lens of the eye, and then it will move through this patch of cells, which is what we call the retina. So you have the retinal ganglion cells in the first layer, the amacrine cell, the bipolar cells, the horizontal cell, and then the receptor. So it's weird because the receptor are kind of buried down, right, on the back of the hairball. But this is where the actual transmission of the signal goes. Now, the disclaimer, the retina is weird. In other part of the brain, when something reacts to an input, it gets depolarized and then you have an action potential. On the retina, it's the contrary. The cones and rod are always on, so they will always output stuff. The only time that they won't output is when they're activated by light, which is a bit counterintuitive, and this will render the whole explanation a bit weird. So they get activated by light, which means that they get hyperpolarized, so they don't send as much neurotransmitter down the line, which will act on the horizontal cell, and then the horizontal cell will become more hyperpolarized. And when they do that, they will actually depolarize the cones and the rods. If we don't think about the hyperpolarization and depolarization, when a cone and a rod get activated, they will activate the horizontal cell, and then that will deactivate the whole patch that is attached to the horizontal cell. Now flip this, and this is what's happening. Now when we're at the second layer, what happens is that the cones and rod will act on both the horizontal cell and the bipolar cells, and the bipolar cells kind of relay the information down the line, but they don't just do that, they do other stuff. And there are multiple versions of the bipolar cell. They are on and off bipolar cells, but that doesn't really matter now, because what they will do is they will interact with the amacrine cell and the retinal ganglion cell. So the amacrine cell job here is to do the same thing that the horizontal cell did to the bipolar cells. So they will, when they get activated, which can or cannot mean multiple things, hyperpolarization or depolarization, they will reduce the activity of the patch of cell that they are working on, right? So if one bipolar cell is activated, it will deactivate the whole patch, which is done by the amacrine cell. Finally, the bipolar cell activity will activate the retinal ganglion cell, which has on and off retinal ganglion cells too. So the retinal ganglion cell react to a patch of bipolar cells, which are given by many cones, and then they will send out their impulse to the optic nerve. The lateral inhibition here happen at two levels, so the horizontal cell and the amacrine cell. So their job is really to reduce the signal to noise ratio and to do some pre-processing, sharpen the image, reduce the blurriness. So if we take a look back at the formula, the horizontal cell and the amacrine cell, they are doing this later stuff over here. So if, let's say, an horizontal cell is connected to 20 rods, the n over here will be 20, so the normalization will happen over a patch of 20 cells. So if let's say one particular neuron is getting activated more than, let's say, the other ones, what will happen is that the division will be less important for it compared to the other one, which will be like depolarized, so less activated. This is kind of what's happening. However, there's a slight difference. In the horizontal cell, it's actually subtracting the mean also, the mean activation, which is more a contrast normalization than a brightness normalization. But this is a detail, but this is what's happening in general. So it's a bit unclear if the lateral inhibition is actually happening in the visual cortex. We know it happened in different parts of the cortex, but in the visual system it's still not 100% validated that this is what's happening. So we're only really sure that it's happening at the level of the retina. So we have two layers that we know are actually doing the lateral inhibition, which is a nice touch, because if you look at the AlexNet architecture, the first two layers are the only one that have the local response normalization, which might be because they tried to model this as the first layer as the outer retina and the second layer as the inner retina, and the other layer being actually inside the cortex. But we know. But this is a nice touch I found. Right, so that's it. It's really a simplification that I've done, but the gist of it is that there are some cells that are actually doing something similar directly in the retina, which is a part of the processing unit for the visual system. If you want to learn more about this, go into the reference. There's 3 really great paper about this. It will give you more details about all the intricacy of this whole system. And if you have questions or comments, you can leave them in the comment section. And have a great week.